So today we discuss AC voltage applied to a capacitor. Discuss AC voltage applied to a capacitor. Okay. So here previous class we discussed AC voltage applied to an inductor, then AC voltage applied to a resistor. Okay. So today AC voltage applied to a capacitor, and that capacitor are in series. Okay. So circuit is look like this. AC voltage source, so capacitor in series. Okay. So that's the EMF, and that's the potential, that is V equal to Vm maximum voltage sine omega t. Okay. So charge stored in capacitor, that is a Q amount of charge stored in capacitor. This capacitor store Q amount of charge. So now solving with the help of KVL, applying KVL in that loop. So here applying KVL. So that is EMF, that's a function of T, that is equal to Q by C. So potential drop across capacitor, that is Q by C. And that is EMF of function of T, that is equal to Vm sine omega T Q by C. Okay. So Q equal to CVm sine omega T. So there is a charge stored in capacitor. So here is the relation. So current I equal to dq by dt. So here differentiate with respect to time. This equation differentiate with respect to time, that is dq dt, CVm constant, the maximum voltage, okay, and C the capacitance, that is sine, differentiation of sine, that is cos omega t, and now the omega is constant, so outside here, okay. So now we get I, said dq by dt, that is equal to I, that is equal to omega c Vm cos omega t. Okay. So here we know that the basic of AC current, that is I equal to Im. So if I input Vm sin omega t, that is obviously a sin omega t. So now the trigonometric ratio here cos now convert to sin. Similar Im, if I compare these two equations, Im equal to omega c Vm. So we get Im maximum current, that is equal to omega frequency, C capacitance, the maximum voltage. And here the capacitor is obviously a passive device but frequency dependent. Frequency dependent like a inductor. Okay. So that's why there is a frequency. So from Ohm's law, that is equal to Im by omega C, that is equal to Vm, and that is equal to, from Ohm's law you know that V equal to IR. So here is that XC. This term is XC, that is equal to 1 by omega C. So XC is almost look like a resistor, but in case of capacitors they are frequency dependent. So these are called capacitive reactance. These are called reactance. Also these are behave as a resistor in that circuit. Okay, as a resistor. So SI unit is ohm. Keep in mind. Okay, this is the SI unit is ohm, and now so that's a final expression. So that we get Vm equal to Im XC. Okay. So here is also convert. We get maximum current. Now the cos here convert to sine. So from trigonometric, with the help of trigonometry, we solve that cos omega t, that is equal to sine omega t plus pi by 2. So now next page. So I equal to omega c Vm, and now this cos omega t convert here sin omega t plus pi by 2. Okay, so here the potential V equal to, that's a V m sin omega t. Okay, and these are called, obviously these are the maximum current Im, represent the Im maximum current if I compare these two. Okay, so here we see that these two equations, look at carefully very, these two equations, the equation is V equal to Vm sin omega t and I equal to Im sin omega t plus pi by 2. Here the current is pi by 2 ahead of voltage. Okay, so here we draw a phasor diagram. Draw a phasor diagram with the help of these. Draw a phasor diagram. Okay. So look at the phasor diagram. Okay. Now, so red color represents the voltage phasor. So voltage phasor is look like this. Is a voltage phasor V, and now the current phasor, this purple color represents current phasor. That's the current phasor I. And you see that current is pi by 2 ahead of voltage. So okay, so that is the pi by 2, and if that angle is omega t1, suppose say that is omega t1. Okay, so here we get a I current. Okay, so here I equal to Im sin omega t1 plus pi by 2, and here the potential is V equal to Vm sin omega t1. Okay, now so these extend here in that direction. So here the voltage phasor, so rotation here, there's a maximum. These are the maximum point here. These are the max point. Okay, from origin, these are the max. Suppose here is down, here is max. So this, what? This. So diagram is look like this. It will be difficult. Okay, that's the voltage phasor. So now the current phasor look like this. Current, okay, so these are the max point of current here. This line, a current here. Okay, now there's the 0. Here is a pi by 2. Here is pi. There at that point that is 3 pi by 2. That's 2 pi. So current is now look like this. Okay, that's the current. The current. That's the I. Red color represent V. And now the cut point here. At cutting point, here is another cutting point. This line, that is a omega t1. That's a phasor diagram. Okay. Here you see that is current is ahead of pi by 2. So current is leading here. Okay. And voltage here with respect to current is lagging. So current is leading by pi by 2 90 degree. Okay. So obviously current is leading with respect to voltage. Okay, that's the basic phasor diagram for understanding current and voltage. So here comparison to that inductor, so inductor's current is lagging pi by 2 with respect to voltage. Here current is leading pi by 2 same 90 degree with respect to voltage. Now calculate power. The basic that calculate power, that is V times I. Okay, so V equal to Vm sin omega t. Here is I also equal to Im sin omega t plus pi by 2. So sin omega t plus pi by 2. So Vm Im sin omega t. So here cos omega t by 2 multiplied by 2. So Vm Im by 2, that is sin twice omega t. So the average power. Okay. Now, so Vm Im by 2 sin twice omega t. So full cycle integration, if that is a function of t, ft, okay, and the full cycle integration, so 0 to t sin twice omega t by t, so we get 0. Previous class I solved this integration, okay, please check that. Okay, we solve this, so here we skip that part. So we get final answer, the average power. So P average, that is equal to 0 times anything, to get 0 watt. Okay. So that's the basic of AC voltage applied to a capacitor. Okay. If you have any doubt, please ask in comment section. So today end the class here. So next class we discuss AC voltage applied to a series LCR circuit. That's very important. Okay. Thank you.